All right, everybody, welcome to class. I know it's been kind of an adventure so far on Project 4. Fortunately, almost everyone in the room has come by my office at some point and gotten some assistance, which is great. I'm going to talk about a couple of minor issues before we survey you all and see where you're at, and then we'll, based on that, go over some other stuff in some more detail. Java keeps randomly changing things on us. I've taught in Java for many years, and so I've got all of these assignments that I've used for a number of years, and suddenly you're in Java 12 or whatever, and stuff just starts breaking. They introduced module info.java. I haven't honestly had the time or interest to figure out what precisely they're doing with it, but there it is. And make sure you've got this file with these lines. I think just about everybody's figured this out at this point, yeah.
Does Java use shared language?
Yeah, it does. Yeah.
This was like a requirement for the different packages you have to have.
Yeah. So the requires lines are like, what are the shared external libraries you're using? Opens lines are like, what are the packages within which you're going to have them access anything? That said, when I was prepping this assignment, I got as far as this, but I didn't include line 7, and it worked fine for me. And then suddenly everybody started dying with on theirs without this line. So anyway, yeah, Java is doing things. Go figure. All right. So I'm going to go ahead then and kind of go around the room surveying where you're at, where you've gotten, what have you seen so far. The goal for today was to get the neural network infrastructure working, to get it going for 2 letters and to see how it did. Not everybody achieved the goal, which is fine, but just go ahead and talk about how far did you get, and then once we've gone over all of these, we're going to take our time going over questions that people might have. So we'll just start right here.
Okay. So I got all the way, I've got the infrastructure set up and everything.
Cool.
I ran my test with the letters S and L.
Okay.
Because I really expected them to have no correlation whatsoever. They're completely different letters.
Okay.
And my neural network got 41 out of 43, so 95.35.
All right. And was it fairly balanced? Like, did it do each of the letters about equally?
Mm-hmm.
Cool. Great start. Innocent.
I also had the infrastructure working, and I was testing letters X and Y. My neural network is predicting Y 100% correct, but X, for some reason, it's not doing anything. I don't know what's wrong.
So it's about 50%. So actually, yeah, okay, so that sounds good. We'll go back and put some of the other details later. Yeah, Dan, what do you got?
I got it working, and I was using A's and D's.
Okay.
And got 100% on both of them.
Sweet.
And I even dropped it down to 500 relations, and I still got 100%.
Okay. Fantastic. Austin.
I haven't finished yet, but I am working on the Perceptron trainer right now. I have one error, small error. That
Yep. 1 error to go.
Yeah.
Cool. Eric.
So I got it working, and I also did X's and Y's. And I made a very explicit attempt to make it as hard as possible, have them all over the place, have different types of Y sound, lowercase y and uppercase Y. And it's 54% accurate, even with a lot more iterations and a lot more.
Okay. Interesting. Yeah, it'll be fun to give that a look. Caleb, what do you got?
Well, as of today, I'm still at the point of getting kind of Perceptron
Okay.
working. The trainer. That module thing came in a little late yesterday, so I was butting my head up against the wall, and then I figured out that I can figure out my errors.
Okay. Jake.
I am working on Perceptron 2
Mm-hmm.
and fixing some errors in there. Hopefully.
Okay. Cool. Will.
Working on the Recognizer AI and the little encoder decoder part.
Okay. David.
So I got working, I did X's and Y's as Well, for the X, I got 90%, the Y, I got 63%. So
Interesting.
it's not 76% overall. But
Yeah.
I think it was because I was very explicit in my X's,
Mhm.
and then my Y's were like,
All right. Mitchell.
I think I've got my perception working. About that is my
Okay, cool. Fish.
I am starting on working through the encoding. I'm anticipating using A's versus Y's,
Okay.
just because they have lots of different kinds.
Cool. So let's talk a little bit about what we can glean from some of these results. Then we're going to take a deep dive through the code infrastructure. In particular, I had a great conversation with one student who was like, I got all the infrastructure working, but it still doesn't actually make sense. And so we're going to spend a lot of time today making sense of it as well. So one thing that can really affect the performance of the multi-layer perceptron is the number of these hidden nodes. Now, you might look at it and say, well, if the number of hidden nodes can really affect performance, well, why not just have a lot of them, right? Why not hidden node your way to success in all possible imaginations? Here's the thing. If we have too many hidden nodes, we can get into a phenomenon known as overtraining. That is, if the number of hidden nodes gets too large, we can have enough distinct edges in the network such that it effectively converges sets of weights that precisely encode all of your training inputs. If you've got enough hidden nodes, you can make enough weights so that all of your training inputs are effectively memorized. So what do I mean by this? Let's imagine that you've got, I don't know, 4 distinct inputs, right? So you've got 2 input nodes. So we can try to think about how many hidden nodes would we need for it to memorize all possibilities? Well, if we've only got 1 hidden node, and you've got something coming in here, something in there, it's certainly not going to be memorizing everything. What about 2 hidden nodes? Well, let's think about the significance of these different edges. You could imagine saying, well, this edge is always going to be a 1 when this is a 1, and a 0 when this is a 0. Or I'm sorry, this edge, this edge is a 1 when it's a 1, it's a 0 when it's a 0. And then do the same thing with this edge. It's a 1 if it's a 1, it's a 0 if it's a 0. And that's still not quite enough, but we could add more. Let's go to 4. Oh, and of course, this. So now we're in a really interesting spot. For each of these hidden nodes, we could imagine it specializing on a specific input combination. So imagine, for instance, that this node is the 1, 1. That is, when we look at these two, you know what? I should actually do something I've never done before with this computer, and I should use the colors. So here we go. I'm going to try red. Let's see how this works. There we go. Yeah, that's a lot easier to see. Okay. So let's say that this hidden node winds up specializing on the 1, 1 situation. So in other words, we pick a weight such that this comes in as a 1 if this thing over here is a 1 and a 0 otherwise. Then we do the same thing here. Next, we could imagine this one specializes on 1, 0. So in other words, this weight is going to look a lot like this one up here. But then this weight is going to be active if a 0 is coming in. In other words, you can imagine that it's like a -1, for example. Or, it effectively performs some kind of a NOT operation. And we do the same throughout. We got 0, 1 over here, and then 0, 0 over here. And so each of these weights is able to specialize in a way that triggers a particular outcome. So, and I should mention, by the way, part of what enables this to happen is having as well the presence of the bias weight that's going into each of these. Okay. So at this point, what we have is a network that's overtrained. That is, at each hidden node, it's effectively memorized an input. And by memorizing that input, it works great on what you trained it with. But if you test it with stuff it hasn't seen before, it's going to be less great. Okay? So that's a problem. From this example, we can see that the number of hidden nodes we have should be, so the number of hidden nodes should be less than the number of training inputs. Once it hits the number of training inputs, it becomes tempted to memorize rather than to generalize, which is what we really want the multi-layer perceptron to do. We want it to be able to predict things it hasn't really seen before. So to this end, we also can't have too few hidden nodes. And this gets at part of what Eric was experimenting with the super crazy Ys and so forth, right? So if you have a lot of heterogeneity within the input space associated with a specific image, what can happen is if you don't have enough hidden nodes, it doesn't have enough representation within the network to be able to distinguish them. So when you get in a situation like that, what one should start doing is start experimenting with raising the number of hidden nodes to see, can I add more representational capacity within the network so that it's actually got a chance at this stuff? Because a lot of what happens in practice, right, is that we can have a category like the letter Y, but really within that category, we might have multiple families of images. So you might have family 1, family 2, family 3, that all kind of have some stuff in common with each other, but really don't have much in common with some of the other families that are associated with that same label. So that in turn then just requires us to think about how do we increase the hidden nodes to compensate. Yes?
Is it possible to combat that in a way where you have like a neural network, it does its thing, you save all of its weights and biases somewhere, then you add some more extra nodes and you bring those back with those extra nodes that are just like don't have anything, and you retrain it that way? Or is that just like not really doing anything?
I mean, you can do it. Effectively, it's like saying, well, let's just kind of train it in phases, right? So you have a first phase with a smaller number of hidden nodes. You see how it does. If you're not happy with it, sure, you can keep them around, bring in another. The question then arises, why are we keeping them around? Like what may happen is those hidden nodes haven't really been able to specialize on particular image features because they're being asked to do more work than they're capable of. And so then that, I mean, it's, as with anything in this realm, it's always worth an experiment. And part of what makes it worth an experiment is that it's fundamentally guesswork to figure out what the network's going to do in response. That's just my informed guesswork as to how it would do. So that's something to think about when we look at this stuff, is making sure you've got a network architecture that's robust enough for the types of inputs that are coming in. And you often can't figure that out until you've tried it. Certainly not in my experience. You really have to test things and see how they look. Cool. Any questions so far before I'm going to go and do a deep review of the whole code infrastructure to make sure everybody's on the same page with how it works? Yes?
For submission, do you want us to include our testing sets?
Yeah.
Okay.
Yeah. Oh, definitely. Yeah. 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 I definitely want your data. Yeah, Innocent.
How do we change the number of hidden layers on this UI? I don't think there is any input box.
There isn't, and that'll be part of what I go over with you in the code infrastructure. Yeah. All right. Any other questions before we do a dive into the code? All right, let's go. So, at the root of it all, we have Perceptron. And so in Perceptron, you've been assigned to do compute and apply weight updates. Aficionados of linear algebra, of which there are a few in this class, have pointed out to me that apply weight updates is a matrix addition. And if you point that out, you would, of course, be right. That's what it is. Thinking of it in terms of matrix operations is a really nice shorthand. That said, I do want to definitely make it accessible to anybody who hasn't had linear algebra, since it's not a prerequisite for the class. But yeah, that's basically a matrix add. You're just adding elements piecewise. Compute, again, for linear algebra aficionados, is a matrix multiplication. You've got the weight matrix on the left, the input vector on the right, and it creates an output vector. Something interesting that came up in some of my office hours conversations here that I'd like to discuss with you all is the whole notion of thinking about a perceptron. What is the data structure? That is, I was talking to some students who were kind of like, well, I can see where the weights are, but where are these and where are these? And so something that's really important to grasp about this as a data structure is that it's one graph, but it's really three distinct data structures, okay? One data structure we're working with is the weights. So in other words, the weights are how the inputs and outputs are connected. And that's distinct from a specific set of input values that are presented to the network. For a given set of weights, many different possibilities exist for a set of input values that are processed through the network. And then that leads to the third data structure, of course, which is the outputs. So the outputs, of course, depend on the inputs and the weights, but are really its own thing in terms of how it's stored and managed in RAM. So with this in mind, we can look back at the code. Oops. The Perceptron class is really all about representing the weights. That's all this is. When we think about the graph, this is only the edges. This is only the edges. When we call compute, okay, I'm flying a little too fast through. When we call compute, we have an array of inputs. Those are the input nodes. And it generates an array of doubles. Those are the output node values. So we see all three data structures come together in compute. And in a deeper sense, that gives us the full network effect. Any questions about the structure of the code in Perceptron? One thing I should add. I'm going to take you to the constructor. So in the constructor, it takes as parameters the number of inputs and the number of outputs. Okay, that's fine. Then it creates the weight array, and num outputs is sitting happily over here. But then there's something kind of mysterious over here. Get num input paths. And then if you do a little poking around, you find num input paths is the num of inputs plus 1. So what's the deal with that? Essentially, the deal is I needed somewhere to stash the weight coming in from the threshold input, the -1. And on an expedient level, it's convenient to have it as part of the same 2D array. Conceptually, we could have envisioned having all of those weights being like their own one-dimensional array just kind of hanging around. That leads to some code complexity later. Basically, there's going to be the complexity. It's just kind of a matter of where it shows up. So weights of the number of inputs is where all of the -1 weights are hanging out, waiting for their outputs. And I've gone over this with a number of you individually, but that's the way that this particular data structure got set up. Cool. Any questions about perceptron? All right, so we're going to look now at perceptron trainer. So let's go over the structure of this in some detail. A perceptron trainer represents two things: a trainee, that is a perceptron that's getting trained, and the inputs and targets. Now, one reason for this setup is that unlike what we did with naive Bayes and k-nearest neighbor, where for a given training example, we just sort of gave it to the data structure once, it used it, bam, it was done. Training of the perceptron family just doesn't work that way. And the reason it doesn't work that way is that getting all of the weights to converge in the network requires a large number of incremental updates. We can't just throw one thing at it and say, great, you're all set. We have to do this very slowly and incrementally. The reason for this is that, especially once we get to the 2-layer perceptron, training it is a very delicate problem. For the 1-layer perceptron, it turns out the training process can be guaranteed to converge. For the 2-layer perceptron, so this is the price we pay for going to 2 layers, you're not guaranteed that it's going to converge at a best possible network. And if you found a way to guarantee that, you will have solved the P versus NP problem in computer science. That is, finding the perfect set of weights for a given set of training inputs requires, the best known algorithm for it requires exponential time. We don't know if that's the best possible, but nobody's ever come up with anything. And it's in this equivalence class of problems where if you came up with a fast solution for one of them, it would actually apply to all of them. So more on that in algorithms and theory of computation. It's just safe to say we don't actually have a guarantee of getting there. So a common aspect of our solution is to not do anything too drastic, right? We want to move the weights slowly. And furthermore, we want to give every training input an equal say in how it changes. So a training input that happens later on, if we were to update all of the weights immediately every time, would be more influential than something that arrived earlier. And that leads to an important aspect of its design, which I'll now show you. So train 1 iteration takes as a single parameter the learning rate. And much like the number of hidden nodes, there's no particular way on the UI to specify it. And so just trust me that I'll be showing you that way in a few minutes. Okay? So when you train 1 iteration, what happens? We set up a 2-dimensional array of pending weight updates. So these are weights we ultimately plan to apply to the network once we're done. Done with what exactly? Done with asking every training input, how did this network perform for what you want? Okay? How did the network perform for the direction you're trying to move it? You can imagine all of these training examples in a fierce battle between each other to influence how the weights change in the network. They're all constantly fighting it out with each other. So what we do here is we create a level playing field for the battle. That is, each training input gets to essentially vote for what it wants for each weight in this array before we actually change the network. And when we do that once, we then do another pass and do it again and keep going. You might wonder, how long do you need to keep going? And I would say, excellent question. And then I would be quiet. So there's obviously a relationship between the learning rate and the number of iterations that you need to make. If you've got a tiny learning rate, you're probably going to need more iterations to get the amount of change that you want. With a big learning rate, you would go with a smaller number of iterations. But what's the right combination? My answer would be, try it. Tell me how it goes. There's no particular set of values that are guaranteed to work. And getting comfortable with that reality is one of the key capacities to develop for an aspiring machine learning engineer. Over time, with different types of data sets and the like, of course, with experience, you can be better informed, but there's no single generic answer that you can just use. Okay, so we've recorded all of our weight updates. We got votes from every training sample. So now we apply the weight updates. That is, we take these votes and add them to the weights that are currently in place, and then they get to change. What were the weights initially, you might be wondering? Turns out they are completely random in the bound -1 to 1. Why not just set them all up at 0? Well, when you start multiplying your errors by 0, you don't get much interesting change. So we just give them some random initial values so that it can do something interesting. We're not really doing this on this assignment, but something that is sometimes done in practice is to actually change the learning rate over the course of the process. So you can do something like, say, my learning rate is, say, based on the number of iterations so far. So early on, you would have a really high learning rate to quickly obliterate these random values that have no meaning. As training proceeds, you would then gradually decrease the learning rate until when you get towards the end, it's actually very small to do fine adjustments. And that's also a practice that can be useful. It's standard practice for the next kind of neural network you're going to look at, the self-organizing map, which we're going to look at next week. Yes?
So how does the running rate of the value like affect the overall training process of the network? Like, is it a constant to compare to weights, and why do we need it?
Okay, so we need the learning rate because if we don't have a learning rate, the network is going to tend to vacillate, jump between different outcomes. You know, if we're just keep slapping errors into the weights, the numbers are so big that the network will have a hard time converging at all. So that can inhibit it from learning successfully. So we need a learning rate to kind of keep those swings under control and help it gradually converge on a value. Right. I mean, it could work in principle with a 1, or if you wanted to be really insane, a 10 or a 20, you know, or whatever. In practice, it really won't. It's just going to jump around way too much. Yeah. And so that's why we have a learning rate.
What is the standard value for running rate?
So it has to be between 0 and 1. You know, if the learning rate is 0, then it's never going to train anything. So it's typically between 0 and 1. I personally like to use values like 0.1 or 0.2 as starting points. And then if my network is having trouble converging, I might lower them to, you know, 0.05, 0.01 or whatever, with a concomitant increase in the number of iterations. Yeah. Good question. Good question. Okay. So getting back to the trainer then. So that's the phases. We find out what the various input samples want, and then we incorporate them into the network. So how do we find out what they want? So this is code I provided. We just have a loop that visits every training sample. For every training sample, it grabs its inputs and its targets. And then it calculates the outputs by calling compute on the perceptron we're training with that given set of inputs. So once we've called compute, we've actually got something to work with. So let me make this bigger. So what do I mean by that? We're going to call record perceptron weight update. So we're going to say, here are the updates we're working with. Here's our learning rate. And by the way, here are the inputs, outputs, and targets that we're employing. So that scoots us down here, where I employed what's called a lambda expression in Java. That is, what I want is for record wait update to be useful even once we get to the multiple levels. But once we get to more than one level, we need a different error function. We can't use the same error function. So the solution then was to make the error function a parameter. So the function itself is a parameter. It takes an integer representing which output you're working on and returns a double representing what the error is. So what we do initially is we tell it, given a certain output, we calculate the error of that output using that output and then the array of outputs and the array of targets. And we call, whoops, sorry, moving around way too much. And notice that that calls calculate error, which you define over here. And I think most of you have that working. The idea here is you subtract, you take the target value, you subtract the actual output, and then you multiply it by the gradient. So what we're doing here is kind of like Newton's method back in calculus, where we use the derivative to help us find a root. So then finally, we get to record wait update. And so the idea here is for every edge from an input to an output, we're figuring out how much does this edge weight need to change so that it does a better job next time. And I think most of you have this going as well at this point. Any questions on Perceptron Trainer and the general Perceptron training process? All right, so now we're going to look at going to 2 levels. So let's do a little sketching here. Common way to draw this is something like this, right? So you've got input, hidden, output. Something like that. As a data structure, what you might say we really have looks a little more like this. And so we've got 2 perceptrons, one after the other, where the outputs of this perceptron serve as the inputs for that perceptron. So looking back at the code, in order to, whoops. Oh, I'm looking at the wrong code. Let's look at the correct code. All right. So perceptron 2, so named for having 2 layers, consists of just 2 perceptrons. Input to hidden and hidden to output. So when we compute, we need to compute the values for both the hidden level and the output. Now, why is that the case? Turns out we're actually going to need these values as part of the training process. So we need a way to access them, to hang on to them. Of course, we also need our output values. And so the solution in the code is to return both of them right there. So the hidden values will be the first element of the duple, and the output values will be the second element. So implementing this was not meant to be a major challenge. This is just a matter of calling compute on each of the 2 perceptrons within it. What do we mean by that? Basically, you got your inputs, you tell this perceptron, compute. That gives you this array of outputs right here, which then become the inputs here, and you then tell hidden to output to compute, and then that gives you those outputs. So then you've got those 2 arrays, you package them up, it's done. If you have a solution that goes more than, say, 4 lines, feel confident that it's wrong. So, whoops, let me do that. So that's compute, and interestingly, that's really all that we need from here. we've got some other stuff for utility purposes. Apply weight updates just takes two sets of weight updates and then applies them appropriately, and so forth. But this is really a pretty thin wrapper over the idea of a single layer perceptron. Where things get a little more crazy is when we train them. So superficially, this is pretty similar. We've got a trainee, which is a perceptron 2, and again, we've got our inputs and our targets. So far, so good. How about training 1 iteration? Well, here things start to get a little more complicated. We need 2 sets of pending weight updates. Why 2 sets of pending weight updates? Because we have 2 perceptrons. So pending weight updates 1 is, what are we going to do to this one? Pending weight updates 2 is, what are we going to do to that one? So, but the structure is again pretty similar. We're going to record our weight updates, and then we're going to apply our weight updates. So let's look at what is involved with these. So record weight updates, I actually provided for you in a complete form. So let's walk through everything that record weight updates does. So as before, of course, we're going to visit every sample, and we're going to grab the inputs and the targets from the sample. So far, so good. Now, what's the process? The first thing we do is we run the input through the entire network. So we call compute hidden and output, which you coded earlier in Perceptron 2. So what have we done at that point? Well, going back to the drawing, we basically said, here are 2 specific input values. That gets us some hidden values, which then become these inputs, and it gets us output values. All right, so far so good. Now, we update the hidden to output perceptron, and we keep its errors. So let's look at this and think about why this is the case. So the first thing we're going to do is we're going to train this perceptron. And to train this perceptron, we actually don't need to do anything different than we already have. What do I mean by this? These hidden values here are the inputs for this perceptron. And of course, we've got the outputs and we've got the errors. So we just feed in these hidden values as the inputs, and it just happily trains as it did. You might be wondering, well, why can't we do that here? Why can't we happily train as we did? And the answer is, we have no target values for the hidden layer. Right? See, when this thing spits something out, we can compare it to our target value. We subtract, we know what the problem is. Over here, we have these values, but they're kind of moving targets, right? Like, what are we supposed to do with these things? So that's a problem. Okay, it's not just a problem, it's like a big problem. Let's make the problem maybe slightly more interesting by giving it, oops, didn't mean for that to be in red. Let's give it a couple more outputs, just to add some tension. So we've got that one, that one, that one, that one, that one, that one. Okay. So now we've got these networks of outputs. So having made this messy, what we can begin to appreciate is that if I've got an error at this output node over here, that error, somebody has to take the blame. And what we do is we distribute the blame among all the hidden nodes. What we do not do is distribute the blame evenly. We are going to be unfair. And the reason we're going to be unfair is that my hidden values have contributed to different degrees to the fact that there's an error. Imagine, for instance, that if some hidden node has a weight coming out here of 0. If it's got a weight coming out here of 0, to what degree is that hidden node contributing to the output? Nothing whatsoever. All of your head shaking is correct. Okay. So consequently, there's no reason to change the weight. If it's not causing an error, we just leave it alone. And that's, again, another reason we don't just set all the weights at 0 initially. It's fine if during the training process it turns out that some hidden node just isn't helping some output and that eventually gets driven to 0. That's effectively the networking sort of correcting for the fact that that edge just didn't even need to be there. Starting it at 0 is not less good though. Okay, so we've established that in order for a hidden node to have some responsibility for the error, that depends on how much of a weight there is. Let's imagine that this had a weight of 100, this had a 10, and this had a 1. The one with the weight of 100 is effectively contributing to 90% of the good and bad of that output node. So if there's an error, the one contributing 100 is getting a lot of the blame. The one contributing 10 is getting less of the blame, and the one contributing 1, well, he's a rounding error at this point. So this gives us the first sense in which we can work out what the errors are here. That is, if I've got some pair hidden and out, there's an edge between them. That edge has a weight. If that output has some error, I'm going to need to multiply it by that weight from the hidden node to the output node in order to assign credit for it. All makes sense so far? But then I also need to make sure that the update is happening in the right direction. So here again, we're applying the Newton's method idea. And so we need to make use of the derivative. That is the partial derivative known as the gradient. So we're going to calculate the gradient of that hidden value. And then we're going to run out of space, so we're going to rewrite it. So weight times error times the gradient of that hidden value. And then this is just our hidden nodes update, right, going to that particular output node, okay? So we're going to need to do this, right, for lots of output nodes. That is, what we're really trying to do is find out how much total error is there coming from this hidden node. We're not changing the weights at this point from the hidden node to the output node. Why? We already did that, right, when we trained that perceptron. What we're looking for here are error values we can use for training this one. So we find ourselves needing to find out not just the result for this hidden to this output, but their sum. So, okay, O is like the dumbest variable name ever. I am actually now trying to think of something worse because I primed myself that way, and I think it is actually not possible. We're going to name this variable out. So we're going to take the sum for every output node of, well, that right there. So what we do is for every hidden node, we visit the edge between it and each output node. We find how much blame did this poor guy get for what went wrong at that output node. And then we're just going to add it to this one. And then we're going to add it to this one. And this sum then gives us our hidden error. So this right here is at the heart of the concept of backpropagation. Let's think about what the term means. First, let's think about the back part. That is, we are working backwards. We get some outputs, we have some targets, we calculate errors. Now they need to go backwards. Why backpropagation? Because we are propagating them backwards. And so this backpropagation of errors is what made the multi-level perceptron possible. That is, they needed a way to talk about what the error even is at the hidden level. And this was the great mid-1980s innovation that made that possible. Is this backpropagation algorithm. And at this point, we're kind of done. Let me show you what I mean. Going back to the code, here we train that other one, the easy part. We keep the errors around because we're going to need them. And now we call record wait update, but here we're going to pass a different error function. So we give it a learning rate, we tell it these are the wait updates we want to update. So here we said we needed to update pending wait updates 2 for that second perceptron. Here we pass in pending wait updates 1 for the first perceptron. We give it the inputs, and then its outputs are just the hidden values. Up here, its inputs were the hidden values, and its outputs were the actual outputs. But we have to do something a little different for training the first perceptron. And so now we're going to tell it, every time you encounter a hidden node, you're going to calculate the error by calling calculate backpropagated error. And so this then is at the heart of what makes it possible to train a multi-level perceptron. So what are we doing here? So the goal is to calculate the error for the hidden node specified by hidden index over here. For each output node to which the hidden node is connected, we multiply the following. In other words, you've got a for loop that's visiting every one of your errors. For every output, you have an error. For every error, you have an output. Right? So for each of those errors, you're going to multiply that error by the gradient of the value of the hidden node and the weight from the hidden to the output node. Then you add them all up and return it. So obviously, we need a very different error function for this layer. But the beauty of this is that once you've got a different error function, recording the weight updates just works the same way. They get multiplied by the input values and the learning rate and so forth. You're just getting the errors differently. Put all those pieces together, and you have a working multi-layer perceptron, which within both my lifetime and memory was a research project, is now a standard issue weapon of machine learning. Any questions on this process before we start talking about encoding? Yeah, Innocent.
Could you go back to the calculate error function, like to see the difference between this one and the one you had earlier?
Over here?
Yes. So here, pass pending updates. So this for the function that you pass as a parameter.
Yeah.
Depending on the layer you are, you pass different parameters.
That's right.
But under the hood, they all do the same operation. Is that what you think?
Well, record wait update always does the same thing. It just leaves us a parameter. Where do my errors come from? That's all.
So these errors, are these errors from like the second perceptron or the last one?
Well, they come from the second one, right? Which is the last one. So looking back at our increasingly messy sketch, the errors come from here. So the errors are known because you know your outputs, you know your targets, you subtract.
Yeah.
You then just train this. We keep these around though because we need them to calculate the errors for this.
Why do we need them on that level? Because I thought
In order to do
assigning the blaming part.
in order to do this, right? We can't assign blame to the hidden node unless we know what the blame is. You know, consider the possibility that the error is 0. We know that if the error is 0, this formula means that none of the hidden edges have to change. And so, at least relative to that output node. Yeah. Good questions. Other questions so far about the back propagation of errors in the multi-level perceptron? All right, cool. We're going to now address encoding and decoding. So this type of a learning data structure can work with any input data and any output data that can be expressed in binary. In other words, literally anything, right, in computing terms. So the next stage of the assignment is to get some practice with doing the encoding and the decoding. Somewhat hilariously, I built the unit test for the image encoding to be over-specialized to my own specific solution. It turns out there's actually more than one way to do it correctly. In fact, there are a lot of ways to do it correctly. And I'll talk about why right now. So let's go ahead and run the drawing editor. So what is a drawing? If I draw a letter like H, what I have here is a two-dimensional Boolean array. And so for my neural network, I need to take that two-dimensional Boolean array and turn it into a one-dimensional array of doubles, right? So one way I could do that would be to march this direction. I could go, give me row 1, and I'll lay out row 1 first. Then give me row 2, and I'll lay out row 2 first. Then give me row 3, and so forth. This is known as a row major representation of a two-dimensional array. But you know what's also legitimate? Let's go down column 1 and put it in there first. Then let's do column 2 and put it in there next, and so forth. And that is known as a column major arrangement. Now, amusingly, in my solution, I had a column major encoding. A student emailed me confused that his test wasn't passing because ultimately he had a row major encoding. That is to say, my test was unfair. Why was it unfair? Because the only thing that matters about our encoding is that it's always the same, right? There's nothing magic about a particular location in the image lining up in a particular slot in the one-dimensional input array. Yeah, I could do something like encode by taking, bless you, the biggest diagonal first, and then going to this diagonal and kind of going up like that, and then it could come down here and lay it out like that. You might be wondering, well, why would you do that? And my answer would be, I wouldn't. That's too hard to code. Or, obviously, I could code it if I had to. It's not worth the effort to code, right? What I could even do would be do, say, a row major encoding, and then shuffle the array randomly. Now we're getting in trouble, right? Because if I shuffle it randomly every time, now my encoding has varied. Now, I could imagine saying, I'm always going to shuffle it to exactly this configuration every time, and that's perfectly fine. Now, when I mention this, does that bother anybody? That it really doesn't matter the order in which you put this in the array? Why does it bother you, Eric?
Because if you just shuffle up a letter and then show it to a person, they're not going to figure out what the original letter was.
Absolutely not. So does it just make you feel like there's something deeply, deeply wrong about what we're doing?
Yeah.
Yeah. And of course, you'd be right. What we're doing is we're throwing away pertinent information. That is, the physical proximity of the pixels is actually information. This type of encoding discards that information. So you might wonder, well, what can you do about it? And I would say, wait 2 weeks. You know, we're going to address this. Yes.
Doesn't it keep the proximity of the data just by the fact that, like, if you're going through zeros and ones,
Yeah.
if you've done a row encoding, when you get to, I don't know, row 4 or whatever, and you put the 1 in for the start
Right.
page, and then you have the 0, 0, 0, 0 until you get to the next one, isn't that capturing the proximity? And the fact that it's doing it in order when it comes across the next row,
Well,
the proximity can be reassembled.
in principle, but here are a couple of problems with that. The first problem is we've lost vertical proximity completely. The second problem is there's nothing about the structure of the perceptron that does anything to leverage that proximity, which is one reason why we're willing to do this kind of an encoding scheme. You know, because ultimately each input node just sort of gets connected to these hidden guys, and it can try to rebuild some of that proximity if a hidden node notices, you know, this confluence of pixels seems to mean something. But we're really asking it to do an awful lot at that point. So it kind of comes back around to something of what Eric was pointing out about the fact that if you scramble it, a human wouldn't recognize it, but suddenly the algorithm does. You know, indicates that ultimately we need to figure out what's something structural we can do to clean this up. So we'll get to that. We're not actually going to code one, but we're going to talk about all the concepts behind it. It's what's called a convolutional neural network. Has some ways of dealing with this, but we're going to master this basic form first before we even talk about that. So in any event, that's what we're doing for the encoding, is this shuffle of the pixels into the code. So let me show you where that happens. So a bridge between all of the drawing code and this other stuff is an interface called Recognizer AI. So I mentioned I'll give you some extra bonus points if you want to code up a different Recognizer AI for, say, KNN or naive Bayes and see how it does against your neural network. If you feel, you know, so you're not required to do that, but I'll definitely give a bonus if you do, because I think it'll be pretty entertaining to see. So a Recognizer AI just needs a method to train. So you give it some sample data, or actually it's just the train n thing. Oh, train n progress. Where'd that go? Oh, of course, that was from our perceptron to trainer. Whoops, I've got another class in. The perceptron to trainer, right? So to have a recognizer AI, you tell it, here's the sample data, and I actually set things up so that it would do a progress bar for convenience. So you don't have to code the progress bar. I took care of that. Obviously, I had fun doing that. Anyway, so you give it a way to train and you give it a way to classify. So how do we classify? We take our perceptron and we tell it to compute based on calling encode sample. And then we get a result back that we then have to decode. So here is encode sample. You're going to get a drawing. You're going to return an array of doubles. Again, this is a very straightforward nested loop. You can go row major, column major, whatever. It'll be fine. What the unit test now tests is to make sure you have the correct number of ones and zeros in your output. And so that's all the encoding process is about. Take a drawing, turn it into ones and zeros. How about decoding? Decoding is in a way a bit trickier. Let's talk about what it involves. So let's say you've got your network. And let's say the network, well, okay, that was stupid. Sorry. Okay, I got everybody. All right. So let's say your network has two outputs. We need to turn the idea of these output values into a category label. Here is a very basic scheme to do this. If you have n labels, what you want is n output nodes. Okay? So you've got a data structure then that will associate, say, this one with the letter A, this one with the letter X. Then what you can do is scan the output values and find the index of the output value that's biggest. Whichever one that is, you decide that is the label that the network is voting for. So again, looking at the code, where you are going to handle this is in label encoder decoder. So I've set most of this up for you. In particular, I've actually built in code. So the idea of encode is give it a string. And in its data structures, it just keeps a counter for how many it's had so far, and then stores in this tree map, given this label, this is the index that I'll use for my encoding. So the first thing you add is A is going to be 0. The next thing you add is X is going to be 1. If the next thing you add is Q is going to be 2. And that's how it's going to proceed. So you do all that, and it'll spit back an array. Okay, not a problem, but now we've got decoding. So given some outputs from the network, we need to find the string that corresponds to it. That I have left as an exercise for you all. Not super hard, but I want you to understand the role that decoding plays in building an actual deployed structure. And this will be a way for you to learn to grasp that aspect of the process. Again, not all that difficult, but we'll make sure that you grasp what the underlying ideas are. Now, you might be wondering, are there other ways to decode? And you'd be right, there are. For instance, instead of n labels giving n output nodes, you could have n labels, and then you could do log 2n output nodes. In other words, you take these label indices and you turn them into binary numbers that you want your output nodes to spit out. That can also work. It can also require a drastic escalation of the number of hidden nodes in the network. Because if you've got, say you've got 4 of these, right? So you've got 1, 1, 0, 1, 1, 0, and 0, 0. Well, if you look at these 4 categories, and if you actually believe me that that was a 1, sorry. There we go. What you find is that you're demanding a 1 on the output for both of these labels, even if they don't really have anything in common. So as a practical matter, you wind up having to escalate the number of hidden nodes just so that this overworked output node has a chance to distinguish them. Yes?
I'm trying to think why you might want to do that. Would that be like you want to have uppercase and lowercase letters, and you want to have more than one possible thing it can train in on to give it the same label, or?
I mean, as far as this is concerned, lowercase a and uppercase a are different letters, right? I mean, yeah, you could do, I mean, certainly what Eric was doing is along these lines, right? You could have lower and uppercase in your drawings, but then ultimately they're going to have to be enough hidden nodes to separate those into 2 categories and then unify them. But at least those have the same label. When we're talking about an arrangement like this, things with completely different labels still need kind of this unifying stage to happen. And so I find this kind of encoding scheme places kind of an extra burden on the network, whereas this is both easier to decode and a little easier for the network itself to master. So that's why I'm recommending this particular scheme. So those are all the pieces then with putting all this together. Any questions? Any questions at all? Yeah, Mitchell. Yeah, happy to. So the label encoder decoder has two data structures, an array list of strings and a tree map from strings to integers. When we encode something, we first check to see, is it a key in the tree map? Let's say it's not. What we're then going to do is put that label in the tree map with the value being the size of this array over here. So the very first time this happens, it hasn't seen anything. It adds its first label. That size is 0, and so then that one is considered number 0. I add a second one. The size is now 1. That's now number 1, and so forth. And then I also add it to that array list. Otherwise, the size would never increase. So why do we need both of them? The array list and the tree map represent inverse mappings, right? So you can think of the array list as being like a map from integer to some value. So if I'm given an integer, I use my array list to find out what the label is going to be. If I have a label, I use the tree map to find out what its integer code is. So what encode does then is it asks the tree map, get me the number for that label, and then return the position it would be in the array. And so, or return an array where that position is a 1 and everything else is a 0. So in other words, you're going to be using this a lot to generate target outputs for your neural network. Right? Because what it does is it says, let's create a new output array. At that position, let's stick a 1 and then return the result. And so now I've got this nice array of target values. Make sense so far? Okay. So let's set up a little mapping to make this clearer. Let's say A is 0, B is 1, X is 2, and Q is 3. So now a training sample comes in, and I have to encode two things. I have to encode that letter A image as a big one-dimensional array. And now I need to code this 0 as a smaller one-dimensional array for my output targets. So what I'm going to want to encode it as is 1.0, 0.0, 0.0, 0.0, like that. For 1, I'm going to want, and notice that 0 corresponds to the array index where a 1.0 can be found. So for a 1, I'm going to go 0.0, 1.0, 0.0, 0.0, like that. For 2, I'll go this. And then for 3, I will do this. So that is what this method does right here. And the reason it works this way is whenever you initialize an array of doubles, Java automatically sets them all to 0. So then we just say which one we want is a 1. So that's the encoding process in a nutshell. For decoding then, you get one of these arrays. And now you got to figure out at what index did I get my spike, my highest value. So notice that something that's pretty elegant about this solution is it's robust to some extremely bizarre behavior in the network. Like, let's say the network lights up 2 outputs as high values and everything else is low. Well, because the sigmoid never actually gets to 1, one of them will still be higher than the other. And so it's just going to go with that one. It'll effectively say the only thing that gets to be a 1 is the absolute highest value coming out of the sigmoid. And so there it is. Does that make more sense? Cool. Any other questions? Any other questions? We got 5 minutes, plenty of time for more questions. Yeah, Dan.
Were you gonna talk about how we set the number of hidden notes and stuff like that?
Oh gosh, that was a big omission. Thanks, Dan. All right. Yeah, let's talk about that. So what the GUI does is it looks in the learners package for things it can try on the interface. So if you go over here, you'll find that something called iter 1000 rate 10 hide 20 is sitting around. Now, what would that be? So here is a format you can use to create your networks. It extends Perceptron to Recognizer AI, but all it does is it creates a zero argument constructor that fills in all the pieces. So for this one, I tell it, give it 1,000 iterations, give it a learning rate of 0.1, and give it 20 hidden nodes. So what I encourage you to do is to create a copy of this file for every network training setup you want to do. So from there, what that'll let you do then is you can make a copy of this, you can name it according to this scheme or whatever, which I think is pretty easy to understand. And then you just go in and change those values to be whatever you want. By the time you're done, you might have 20 or 30 of these in there, and that's fine. What's nice about doing it this way is that you've got actual code you can use to replicate an experiment. So if you're just kind of setting them up on the GUI, it might be easy to lose track of, well, how would I reproduce those results? What settings did I have? You'd have to write them down in your notebook or whatever. Here, your settings are right there in the code, just hard-coded in place. And then you can just pick on the drop-down menu which one you want to do. So that's how you're going to do that. That makes sense to everybody? Obviously, if some particular experiment is particularly stupid or pointless, you might just edit it in place and rename it or whatever. You don't have to keep all of them. But you definitely want to keep all the ones you're going to talk about in your paper so that you can reproduce those experiments later on. Yeah. And that turns out to be especially valuable when you think about running larger and larger experiments. So you find a configuration that works really well with 2 letters. Well, you're going to want to use it again with 3. And then you might come up with a modified version, but you want to make some notes that, with 2 letters, this one was good enough. With 3, it turned out I had to do something with the hidden nodes or whatever, right? But this makes the architecture of the training process independent of the specific test case you run as well, which is also really useful. So, cool. Oh, yeah, this confused some people as well. Let me briefly go over actually creating your stuff, right? So what you're going to be creating are files containing specific training and testing sets. So I put a folder on my desktop. You probably want to put it in your package so when you zip it up, I just get it, So I've got 2 files here. I've got AH and AH2, And so I can load up AH, and I say I want to look at index 0. All right, how about index 1? Index 4, those are my A's. And then I can switch over to H. The same kind of thing applies. Then to test it, I would open up test all. Then I come in here and I want to test it with AH2. It turns out I get 0% correct because this network hasn't actually been implemented. And then here's my little result chart. The visualization tab doesn't do anything. We will be using it in the next assignment. So actually the next assignment, I'm going to give you a zip file that you're just going to unzip into this because we're going to do handwriting again next week. Yes? Mm-hmm. It shouldn't do anything good, but it will at least execute. Yeah.
As we start expanding the number of letters, so like right now I've got an AD file.
Yeah.
If I want to add Z into that.
Yeah.
Do you want us to make a brand new file with AD and Z and keep all the iterations, or should we just go back into our AD file and can we start just adding?
I would just go into the AD file. The way the file format is done, you could actually copy the A's back out, and if you wanted to rebuild it, it wouldn't be a problem.
But you're not really worried about when we submit it, if we have all the different iterations of the letters.
No, at that point, it's just more stuff for me to look at. Yeah. Yes.
When you're creating testing and training data, like for AH, you sort of like create like labels and you draw them, like
Yeah.
A and H, and then you save it.
Yeah.
And you create a new file.
Yep.
You do the exact same thing and you save it.
Yep.
But you train on one and test on the other.
That's right. I mean, you're certainly welcome to have it test on itself, and if it does really badly, then you've got a problem. But if it does well, it doesn't really tell you anything because it could have just memorized them.
So my question is, in the previous machine learning algorithm,
Yeah.
for KNN and naive Bayes,
Yeah.
when you are trying to classify something, we didn't give it a label. We just gave it data and it gave it back a label.
Oh, it had label. Oh, this will give you labels too. Like you can actually like draw on this and ask it to classify. It'll give you a label.
In this case, when you're creating a testing data, we still like need to give it a label.
Yes. Well, right. That's just the way this particular. Right. I see what you mean. In principle, the testing data doesn't need a label. In practice, it does, so it can tell you whether it got the test right. But you can do stuff like this. You can just draw something, hit classify, and it'll tell you what it is. In this case, it told us unknown because it's totally unimplemented. That's something fun you can do with this. Once you've got it going, just start drawing in there, hit classify, and see what it thinks it is. Yes?
That would only work for like the 8 or 2, right?
The number that you've trained it on, it's gonna pigeonhole it into one of those. Yeah. It'll find some way to turn your I into an H. If it turns out that an H is a better match than an A or a Q. All right. Have fun with these guys. I will look forward to seeing you all on Thursday. Networks trained, ready to go.